Start recording. There we go. Okay. Laura, I record all the lessons, so if you miss something, it will be on our team, and I will add you to our team as soon as this lesson's done, okay? Okay.
Here is something that might help you think about this. Take a piece of paper. Look at how wide it is here, all right? This is so incredibly thin. Now, atoms are so small that it would take 1 million atoms lined up next to each other in a row to be as thick as this tiny width of paper.
So how many atoms thick is your piece of paper? 1 million atoms. That's a lot. Like, try and imagine that. I can't even imagine something that small. Like, my brain doesn't do that.
That's how small atoms are. Now, what I want to do now is look even closer at an atom. Let's take one of these atoms here and zoom in even more so we can see what's inside of it. Here's a magnified view of one atom. It's not a perfect representation of exactly what an atom would look like, but it's close enough for right now.
Whose model would this be?
It's nuclear model.
This is the nuclear model.
Yeah, I think it's
Who came up with the nuclear model? Rutherford, yes.
And check this out. The atom itself is made up of even smaller things. Right, so that we said atoms are like the building block for all of stuff. But then if you look at an atom, it has even smaller building blocks that make it up.
What are these little black smaller particles? Those are the electrons. What are the blue and red ones? Protons and neutrons. What charge are electrons? Negative. What charge are protons? What charge are neutrons? Neutral. Fantastic. Okay.
So in the center of the atom is something called the nucleus. And the nucleus is made up of two tiny particles. There are protons, which I've drawn as red circles here, and then there are neutrons, which I've drawn as blue circles. Nucleus is here in the middle of the atom.
Now, from your homework, you should have an idea of how much a proton weighs, I believe. How much does a proton weigh? Anyone remember? Yes? What? Yes? What?
sorry.
How much a proton weighs?
1,836.
What?
1,330. Wait, what?
What?
1,836.
No, that's the mass.
Oh, I see. Oh, dang. That makes me unhappy. Because on the other page, right opposite that one, we give the mass of a proton as being 1, which is a nice, easy number, which is why I'm like, what? What are we talking about? So the mass of a proton is 1.
What's this one?
Just go with me, okay? We'll talk more about that later, okay? What is the mass of a neutron?
2.
1. So proton weighs 1, neutron weighs 1, and electrons weigh next to nothing. So we just ignore them, okay? I'm going to let Tyler talk more about that, though.
And then on the outside of the atom, there are these little black circles that I'm using to represent electrons. The electrons, you'll see, are connected to these sort of oval paths, and I've drawn these in to show that the electrons are constantly moving. They're flying around the outside of the atom at an incredibly high speed, whereas the nucleus stays solid here right in the middle of the atom.
Do protons and neutrons move? No. Who moves? Electrons.
Now, electric charge is very important when we're talking about atoms for a number of reasons. Protons have a positive charge. A proton has a charge of 1 plus.
And according to this, oh, this is weird. So here, according to this little model here, we have 1, 2, 3 protons. Normally, how many electrons should we have?
3.
We should normally have 3. So I don't think he's being very careful in this particular model. I think he's just doing a kind of like general shape.
Electrons, on the other hand, have a negative charge. One electron has a charge of 1 minus. Now, neutrons, they don't have an electric charge at all. They have a charge of 0. And neutral is a word that we use to refer to something that doesn't have a charge. So neutrons sounds a lot like neutral. Now, positive and negative charges attract. Remember that? Opposite charges attract. And that has important consequences for how this atom works. We said that these electrons are flying around the outside of the atom. They're moving really fast. So why don't they just fly out into space? Well, the reason why is because the negatively charged electrons are attracted to the positively charged protons. So the protons kind of pull the electrons in. They keep them from just flying away. But the electrons are moving around so fast that they're not able to actually pull in here and actually touch the protons. So that's why they keep staying on the outside and don't just crash in here and all touch the protons. Now, sometimes people ask, well, neutrons don't have a charge. Why are they important at all? Well, it seems...
Why are neutrons important? Well, let's take a look at those little protons. They're all sitting there in the nucleus, all together. What is all of their charges? Positive. What does positive do to positive? They repel. So what would you expect to happen if we put a bunch of protons together? It would explode. So what you know what the neutrons do?
They neutralize.
They keep it from exploding. They actually provide a different force, not an electrical force like the electrostatic force between positive and positive, but they provide a nuclear force which is even stronger.
That neutrons help keep all of the particles in the nucleus strongly connected to each
So they act a little bit like glue, okay, for those protons.
other. Now, electrical charge is important. Something else that's important with atoms is what their mass is, how much they weigh. So in order to figure that out, we have to look at the mass of the various things that make up the atom. Now, a proton and a neutron are very, very similar in size and in mass. And they both weigh about this many grams. Look at what a tiny number this is, right? There's a decimal place all the way over here. This is a number that it's best to represent in scientific notation.
And if any of you did scientific notation way, way back when, what you'll notice is that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We've moved our decimal place 24 places to the right. So that is 10 to the negative 24. If you didn't do scientific notation, that was just a very quick preview of what scientific notation is. You'll learn it in grade 11 if nowhere else. All right, and just before we carry on, let's make sure that we all got everything on that first page. Atoms are the what? They are the building blocks for all matter. Have you guys heard the joke? Atoms are liars. They make up everything. 6, 7. Sigma.
Misfits, just leave it there.
Skibbity.
No, leave it there.
Skibbity Riz? No? Okay. All right. Atoms are super tiny. It would take how many atoms to make up a piece of paper? million. Okay, if we zoom even more, well, atoms are the building blocks. For all stuff, but an atom has even smaller building blocks that make it up. And these smaller building blocks, this is not on your sheet. These are called, these three here, subatomic particles, indeed. I didn't leave room to write particles. Particles. There we go. Subatomic particles. And those three subatomic particles are, what's the top one? Electrons. And the red ones are the protons. And did you notice I fixed the problem for Tyler? Tyler only had 3 protons, but I put 4. Woo-hoo, look at that. And we also have the neutrons. And what do the protons and neutrons together? They make the nucleus. And watch your spelling on that. It is not nucleus. It is nucleus. Nucleus. And also watch your pronunciation. People have a tendency to say nucleus, but that's not it. Nucleus. All right, so we have our electrons, which are negative. We have our protons, which are positive. We have our neutrons, which are neutral. Okay. So the mass of one what? Proton is 1.67 times 10 to the negative 24 grams. And now we're going to go back to the video and see what the rest of these boxes say. Okay?
Instead. But however you write this, it's a really tiny, unwieldy number. So scientists came up with another way.
The word unwieldy means awkward. Okay, unwieldy. Unwieldy. Awkward.
To measure the mass of a proton or neutron, and that's using a unit called the AMU, the atomic mass unit. And
okay, shall we fill that one in? We have 1 AMU. That is an atomic mass unit. So 1 atomic mass unit is equal to 1.67 times 10 to the negative 24 grams, or 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000smaller than a proton or a neutron. It weighs only 0.000549 AMU, so a tiny fraction of how much a proton or a neutron weighs. Okay, so let's fill that in before we forget that number. So the mass of 1 electron weighs 0.000549 AMU. What does AMU stand for?
Atomic mass unit.
Atomic mass units. And we missed something up here. I missed something up here. The mass of one. What did I miss? Proton or neutron. Okay, they both have the same mass, essentially. Close enough anyway. All right, and we can now go to our next page. Oh, no, we can't. There's more stuff at the bottom. An electron weighs a tiny fraction. So to be honest, we usually don't worry about the electrons at all. They are so tiny that they do not affect the mass of an atom much at all. It's like if you go on and you get on a scale to weigh yourself. Do you take off your earrings or your watch or your, glasses or anything like that when you step on a scale to weigh yourself? Do you worry about that? No, because they weigh so little compared to the mass of you. Same thing goes for atoms. We say protons and neutrons weigh a lot, so we count them. Each of them counts for one AMU. Electrons count for so little, we just ignore them when it comes to mass. Okay? Those things are just so small, we can just ignore their mass and focus on the masses of the protons and neutrons. So we ignore the electrons and just focus on the protons and the neutrons. And if you're like, what are these symbols you are drawing, Ms. Spence? E with a little negative means electron. P with a plus means proton. N with a 0 means neutron. So E is electron. P with a plus, proton. N with a 0, neutron. Electrons don't actually go around the nucleus in nice circles. They actually buzz around like hyperactive. Do you guys remember what they buzz around like? Hyperactive flies. And I don't remember the next analogy, so we're going to have to go back to Tyler for that.
For this reason, when we're talking about the MUs, the atom weighs, and then we usually don't even worry about the tiny. They don't really much an atom weighs. It's like when you get on a scale to weigh yourself, how much you weigh, that 1 AMU and electrons, a tiny fraction of that. Now I said that the atom, the way it's drawn here, isn't a perfect representation of what atoms would actually look like. We'll talk more about that later, but there are two things that I want to bring up for right now. The first is the electrons and how they move. This drawing might make you think that the electrons are spinning around in nice circles on the outside of the atom. That's actually not what happens. They're buzzing around much more randomly, kind of like hyperactive flies all over the place. We'll talk more about that later. The second thing has to do with the size of the nucleus and how far the electrons are from it.
The nucleus actually looks pretty big compared with the size of the atom here, yes? Right? It only looks, maybe the atom is about 10 times bigger. That's not how it is at all. Let's find out.
If this were a real atom blown up many, many times, and the nucleus were the size of a grape.
Okay, so we got the nucleus. What's it the size of? Grape.
The electrons out here would be almost a mile away.
The electrons would be a mile away. So the nucleus is the size of a grape. And the electrons, so that means that the entire size of the atoms would be 2 miles in diameter. That's crazy, yes? What does that tell us about most of the atom?
Most of it's
Most of it is, well, it is electrons, but electrons are so small that truly most of the atom is made of empty, I heard someone say it, empty space. Yeah, absolutely. The electrons are buzzing around the outside, but if they don't happen to be in any particular location at any particular time, then you just really don't see them at all. It's just empty space with a few electrons floating around in there. It's like space. Space is mostly empty space, but with a few stars here and there. Okay? So let's fill that out. If the nucleus were the size of a grape, the electrons would make a cloud that reached about a mile away. And if you're not familiar with miles, a mile is about 1.6 kilometers. Okay? Kilometer and a half, yeah. Most of the atom is actually, what was it? Empty space. But that empty space contains electrons that are buzzing around in that empty space. So one moment they're here, the next moment they're there in that empty space. Okay, we are going to skip these questions for now, and we are going to go on to what are isotopes? And this is on page 83.
Isotopes are different versions of an
Ooh, look at you go. Yes, sure. Just sign out. Okay, here we go.
What are isotopes? Isotope is a word that gets thrown around in chemistry.
Okay, hang on. Tyler, stop talking for a moment. I need to rewind you. There we go. That's all the way up. That's all the way up. That's going to be big. Subtitles. Play.
What are isotopes? Isotope is a word that gets thrown around in chemistry a lot. So, what are they? Really quickly, isotopes are different versions of an element, or different versions of a certain kind of atom.
Can you guys even hear
This
this?
can be a tricky concept, though, and a lot of people get confused by isotopes. So I want to describe them by starting out with an analogy to cars, okay? I want to talk to you
Okay, this is going to
about
take a
the
second.
made-up
I apologize
car
for the scratchiness. Okay. Let's try it again.
Okay? I want to talk to you
That did not
about the made-up car called the Lamona, the epitome of luxury, and it's known for its very
Okay, you know what we're going to do? I'm going to mute him, and I'm going to read it. The Lamona, the epitome of luxury, and it is known for its very distinctive styling. As you'll see, the Lamona looks like a lemon. Now, the Lamona comes in 3 different models. The Lamona G, the Lamona GX, and the Lamona GXL. Ooh, they're all different colors. The Lamona G comes with a radio, leather seats, and it is yellow. The Lamona GX comes with chrome wheels and a CD player, because this is a very old video, and it is blue. And the Lamona GXL comes with massaging seats, platinum spinner wheels, and it is red. However, do all of these cars look pretty much the same?
Yeah.
That's because they are all Lamonas. They are all beautiful lemon-shaped cars. And the reason that this is supposedly a funny joke is that a car that doesn't work very well is often called a lemon. So if you buy a car and it breaks down all the time, you have bought yourself a lemon, okay? Anywho, let's carry on with this. Here we go.
Like ice cream or I love those.
So we have the various Lamonas, okay? And they all have different features, but they are all different versions of the Lamona. And I think I can actually take it from here without having Tyler and his quiet thing. Isotopes are different versions of an element. Just like the different models of a car are different models of a particular car, so there are different versions of the Lamona. We are now going to take a look at different versions of the atom. So we're now going to be, did I tell you guys we were on page 83? I did, yay, okay. Here we have various isotopes or versions of the carbon atom. Please have your periodic table out. And I'm going to grab a periodic table here. Has anybody need one need pen? Or if you wish to use just the slides too? Okay. Anyone else need a periodic table? Everyone got one?
Miss Abby.
Ah, there you go, thank you. Go find carbon on your periodic table. If you have trouble finding it, don't forget you can always go on to the back of the periodic table. You can look under C for carbon, and you can say carbon is atomic number. Our atomic number is that third column there. Why is this not going? There we go. Our atomic number is 6, which means that when you go to the other side of the periodic table, you can count across, because the periodic table is in order of atomic number. So you'll see we start with 1, then we have 2, and then we have 3, 4, 5, 6. So you can always find your atom by looking on the back and then finding the atomic number and then just going in sequence. Okay, so here's carbon. I'm just going to rewrite that on here. Carbon, we have the number 6. Okay, so how many protons are in carbon? That is our atomic number, which is equal to the number of protons. So carbon has 6 protons. And if you look at it, we have our little red protons here. 1, 2, 3, 4, 5, 6 protons. Okay? These are all different versions of the carbon atom. Let's look at our next carbon atom. How many protons are in this carbon atom? 1, 2, count them up. 3, 4, 5, 6. And how about the next version of carbon?
1,
2, 3.
4, 5, 6.
What do you notice that all the carbons have in common?
6 protons.
Yes. Yes. What do you notice that all the carbons have in common? They all have 6 protons. Just like all the Lamonas were lemon-shaped, all carbon atoms have 6 protons. It is the number of protons that makes it a carbon atom. If an atom has 6 protons, it is carbon. Doesn't matter how many electrons, doesn't matter how many neutrons. If it has 6 protons, it is carbon. If an atom has 6 protons, it is carbon. And that's why at the top of the periodic table, we can definitely write 6 here. Right? The atomic number, the number of protons, it never changes. What if I added a proton? How many protons would I have?
7 and nitrogen.
I would have 7 protons and it would no longer be carbon. It would now be nitrogen. Okay, so if we change the protons, we change the element. Change the number of protons. Change the element. Now, there's a couple other things we can fill in here together, all right, just from looking at the diagram. This carbon 12, how many neutrons does it have? Let's count them. 1, 2, everybody? 3,
4,
6. What does 6 plus 6 equal? 12. That gives us this number here, this 12, is the protons plus the neutrons. And that is called the mass number. That is not the same as atomic mass. It's close, but it's not. And the reason is, and we'll learn about this tomorrow, or not tomorrow, Monday, is that when you get the atomic mass, it is the average of all of the atoms of carbon in the universe. And we're going to find that not all carbon atoms have a mass of 12. Okay, because let's go to our second carbon atom here, and let's count our neutrons. How many neutrons in this atom? 1, count with me.
3, 4, 5, 6, 7.
We changed the number of neutrons. Oh my gosh. So instead of calling this carbon with a dash and then 12, what would we call it? Carbon, and then a dash, and then 13. Okay? So this 13 right here, that is, what do we call that number? That is called the mass number. And that, what is it equal to? Protons plus neutrons. Okay. Now, while we're here, we got a box right here. And it's got a little arrow pointing to it from the protons. What do we call the number of protons? That is our atomic number. Okay, so the atomic number is the number of protons. The mass number is the protons plus the neutrons. And there's 2 ways of telling us that this is carbon version 12. We can do, right, carbon dash 12. Or we can write the mass number beside the symbol. So instead of writing the whole word, we can write the symbol, just the C. And at the top left, we can write the 12. Okay, so that right there is our mass number. Protons plus neutrons goes at the top. Okay. What goes at the bottom? That's the atomic number. So that is going to be a 6. So how would we write, and this notation here, this one right here, this is called isotope notation. It is also known as nuclear notation. And that's when we put the numbers. Do we put the numbers on the left or the right? We put the numbers on the left of the symbol. Which number goes on top, the bigger number or the smaller number? The bigger number goes on the top. Let's think, if you were like a person who's a bigger deal, would you live in the penthouse or the basement?
The basement, because it's cooler.
Okay, so the bigwig lives in the penthouse, so the big number goes on top, and the smaller number goes on the bottom. You don't even have to think about it that way. You can just think about it like the lower floor has a lower number and the higher floor has a higher number. Okay, so the big number goes on top. Or if you don't want to use the nuclear or isotope notation, you can write the name with a dash and the mass number afterwards. We don't write the number of protons when we're writing the name, okay? Could you fill in the nuclear notation for this version of carbon? What do we call different versions of carbon? This is isotope. This is isotope number 1. Isotope number 1. This is isotope number 2. And this is isotope number 3. I think for carbon, there may be only 3. Some elements have like a ton of different isotopes. Usually the ones that are like bigger masses that will have more different isotopes. Some of them only have 2 isotopes. Okay. What number would we put in the yellow box? Tell your partner, what number would we put in the yellow box? What number goes in the yellow box? What number goes in the yellow box? Yep. 13. Okay, mass number. And what number goes in the bottom box? 6. That bottom number will never change for carbon. It will always be 6. Does the number of neutrons go anywhere? Do I write the number of neutrons? Nope. Just protons plus neutrons. But you can calculate the number of neutrons. And you know what's really nice? Do you know one reason why we write the big number on the top and the small number on the bottom? Because if you go 13 minus 6, you end up with 7 neutrons. If you go 12 minus 6, you get 6 neutrons. So if you have that isotope notation, you can calculate the number of neutrons in a particular isotope. What is the name of isotope number 3? Count your neutrons, figure that out with your partner. Did everyone count 8 neutrons? Okay.
I don't think it's supposed to be.
So what would we name? What would we name this isotope? Carbon dash 14. Now, normally we won't say the word dash, but I want to remind you that there is a dash there. So I keep saying dash, but normally we would just pronounce this carbon 14. Okay? But for now, we're going to say carbon dash 14 until it becomes automatic for you to put that dash in there. And if we wanted to write the nuclear notation, what is the other word for nuclear notation? Isotope notation. How would we do that? Tell your partner. Actually, try it. Try it and see, then check with your partner.
We already did it. Oh, yeah.
What do we got? We got C. Where does the 8 go? Nowhere. Where does the 14 go? Top. Where does the 6 go? Bottom. Left. And if you wanted to calculate the number of neutrons, how would you do it? 14 minus 6 equals 8 neutrons. What is this number called? This is called carbon 14, but what do we call this number at the top? That is our mass number. What is the mass number equal to?
Proton plus neutron.
Protons plus neutrons. What is this 6 called?
Atomic number.
Atomic number. And that is equal to the protons. Okay? All right. Let's try a few others. Here we have calcium. Could you go find calcium on your periodic table for me and find its atomic number?
Oh, that's cool. Right?
Atomic number of calcium is 20. Yes, indeed. What does that tell us? Calcium has 20 protons. Ooh, by the way, how many electrons would a calcium atom have? It would also have 20 electrons. Okay, because the total is 0. You need to have 20 positives and 20 negatives. All right, let's take a look at these here. We're not going to worry about that one because it's all blank. I forget what went there. If you have 20 protons and 24 neutrons, what is the name of that isotope? Calcium. Dash 44. And its isotope notation would be Ca, what goes on top? 44. What goes on the bottom? 20. Very nice. Okay. And there's just some for iron. Okay. Okay, I think we're good. I'm going to give you guys some practice here. Okay. We are going to go to page 89. Let's look at the top of the page. We're going to make a notation here. The atomic number is that top number on the periodic table, but the bottom number is not the mass number. What is it? It's the atomic mass. Another way of saying atomic mass is to say average atomic mass. So that tells me that probably because the atomic mass, the average atomic mass is 28.1, the most common isotope would probably have a mass of what? If the average atomic mass equals 28.1 AMU, what do you think is the mass of the most common isotope? Have a chat with your neighbor about that.
That's the most common isotope. I think it would be because it's the one that's called the average. Yeah. Probably not 3, but
I'm going to give you some choices here.
it can't be 3. I think it's 28, but because there's color between. Yeah, I want to say 29.
So here are your choices. A, 27. B, 28. C, 28.1. D, 29. So what we're saying is most atoms of silicon have a mass of, is it 27? Or do most atoms of silicon have a mass of 28? Or do most atoms of silicon have a mass of 28.1? Or do most atoms of silicon have a mass of 29? And you're going to think about that and chat with your partner, and then we're going to vote. A is, show me A. Okay, show me B. This is B. And everyone should be able to do C because it's really easy. And then D is more difficult. Take your pointer finger and point it up, and then make a circle with the rest of your fingers. So all your rest of your fingers touch your thumb. Pointer finger up, the rest of your fingers touch your thumb. That is a D. Okay? And if you look at it from your perspective, that is a letter D. It looks like a B from the front, but from this perspective, it looks like a D. So pointer finger up, 3 fingers touch your thumb. So is the answer A, B, C, or D? Chat with your neighbor. Decide what you think.
Because they're like 0.1 of that.
Oh, and there is an option E, which is I don't know yet. Okay? It is totally fine to be like, you tell me. You're the one with the degree in science. Come on, Miss Spence. Get with it. That's okay. Are we ready? Okay, 5, 4, 3, 2, vote. I got some I don't knows, I got some B's, I got some C's. All right. Here's the thing. What does 1 proton weigh? 1. What does 1 neutron weigh? 1. Is it possible for an isotope to have a mass with a decimal in it? No. Because you have to have whole numbers only. So you guys, most of you guessed 28, and that's correct. What do you think the mass of one of the other isotopes might be?
29.
Probably 29, because our average is somewhat bigger than 28. Right? Well, the average is 28.1. That's a little bit bigger than 28, right? No? On a number line? 28, 29, 28.1, 28.2, 28.3, 28.4, 28.5, 28.6, 28.7, 28.9,
Oh, that's
29. Yes?
Yeah.
So 28.1 is bigger than 29. So you would have to have some silicon 29 in there as well. Okay? So do not use the atomic mass. Never in grade 9 use atomic mass in grade 9. Other than that lab we just did, and that was just to get you looking at the different parts of the periodic table, never use atomic mass. So you can just ignore that number at the bottom. You will always be either given the mass number or you will be given the number of neutrons. Okay? Never mind, I'm not going to write that down right now. Okay, so let's look at our first table here. Let's try our first one together. Hydrogen. Please find the symbol for hydrogen. Hydrogen is H. What is its atomic number? 1. And what is the number of protons? 1. What do you know about the atomic number and the number of protons? Those two are the same. So those two numbers are always going to be the same. Let us try this one down here. Who has an atomic number of 8? Who has an atomic number of 8? Oxygen, yes. What is the symbol for oxygen? O. And how many protons does oxygen have? 8. Do you guys think you would be able to complete the rest of this table?
Yeah.
Yeah, we're not going to do it right now. We're going to go to the next page, because I want to give you a little bit of time to work on it, but I want you to also be able to do the second table here. Okay, so this is the next table we're going to do. You will either be given the number of neutrons or you will be given the mass number. Do you see how either you have the neutrons or you have the mass number? You have to be given one or the other. Is it possible to find the number of neutrons without the mass number? No. Is it possible to find the mass number without the number of neutrons? So you have to have one or the other. What is mass number equal to? Logan, what's the mass number equal to?
Mass number?
Yeah. It's two particles added together. Do you remember which ones? It's okay if you don't. You know what? It's actually given right here. It is the protons plus the neutrons. So in order to be able to do your homework, make sure that you write down that the mass number is the protons plus the neutrons. Now, how do you calculate the number of neutrons? Yeah, you take your mass number and you subtract the protons. To find neutrons, you subtract the protons. Okay? So you now have the tools to do all the questions on page 89 and 90. So for your homework, it is a weekend. It's going to be a little bit bigger. Let me see.
That's 81 and 90. Or no, 89.
89 and 90 and 17.9. Yep. Still not too much. Okay? 3 pages. You might even be able to get it done in the next 10 minutes.
13. Okay. I forgot. So,